Hello everyone. Today, we come together to learn the relationship between frequency and motor speed in the power system, the principle of regulating frequency, and the situation of load change in the system, and other basic knowledge. I am the main teacher, Liu Qingping. In order to deeply understand the principle of low-frequency, load-shedding devices, let's first learn some basic knowledge of frequency in power system. The first knowledge point is the relationship between the rotational speed of the generator unit and the frequency of the system. According to the other professional knowledge, we can get the following formula. The frequency of each generating unit operating in parallel is equal to the number of pairs of rotor poles of the generating unit P multiplied by the rotation number of the generating unit N and divided by 60. From this relationship, it can be seen that the frequency control of the power system is actually the regulation of the rotational speed of the generating unit. The second knowledge point is the principle of frequency regulation. Let's analyze it from when the system is operating normally and when the load suddenly increases. The first is when the system is operating normally. Assuming that there are M units in the system, then the total input power of the prime mover of each unit is the sum of the input power of M units. This can be calculated using the following equation. The total generating power output of each unit is the sum of the power emitted by M units, that is, Pg1 plus Pg2 plus Pgm. If the time of internal loss of the unit is ignored, the input and output power are balanced. If the load suddenly increases, PL, but due to the mechanical inertia, the input power of the prime mover is too late to respond. This time, the input power of the prime mover is less than all the load. At this time, to maintain the power balance, the unit can only convert parts of the kinetic energy of the generation rotor into electrical power, which forces the unit's rotational speed to drop, and the frequency of the system will drop followed. We can also use this equation to express the power balance relationship, where WKI is the kinetic energy of the rotor of each generating unit. Next, we analyze it according to the torque characteristics of the generating unit. When the system is operating normally, the unit operates stably at point A with rotational speed NA. When the load suddenly increases, the generator electromagnetic torque characteristic curve has to shift upward, assuming that it moves to the position of curve MG2, and if the power element entering the prime mover is not regulated at this time, such as steam or water, the unit governor will not act. The mechanical torque characteristic of the prime mover remains at curve MT1, and the unit will stably operate at the new balance point B at rotational speed mb. This shows that even without a governor to regulate the input power of the prime mover, the unit can transition from one steady state point A to another steady state point B. Then this ability is called self-balancing or regulating ability. However, the rotational speed mb is far from the original rotational speed na, which also indicates that the rotational speed or frequency of the unit will change in a wide range if it is regulated only by a self-balancing ability of the unit. We can get the conclusion from the analysis we just made. The change in the frequency of the power system is caused by the loss of balance between the load carried by the generator and the total power input by the prime mover. The regulation of frequency is inseparable from the regulation of active power. We know that the power system load is always changing, while the input power of the prime mover is changing slowly. So, the frequency fluctuation in the system is very difficult to avoid. Then, since the power system load is constantly changing at any time, let's analyze the changing situation of the power system load. We can categorize the load. One kind of load is a random component with a change period of less than 10 seconds, which can be seen from this figure. That is, the second curve. One kind of load is a pulsating component with a change period between 10 seconds and 3 minutes, and one kind of load is a continuous component with a change period of more than 3 minutes. This is a forecasting part of load prediction, and these three types of loads make up the top load, which is the curve of instantaneous change. Then, for these kinds of loads, we can take different adjustment measures. For example, for the frequency deviation caused by the first kind of load change, we can use the governor to adjust the input power of the prime mover, which is called the primary frequency adjustment. The second kind of load change causes a larger frequency deviation, which must be involved in the control and adjustment by the frequency tuner. This is called the secondary frequency adjustment. The third kind of load change is the scheduled load of the dispatch department, and this is called the triple frequency adjustment. This is the situation of load change. In this lesson, we studied the relationship between frequency and generating unit, rotational speed, the principle of frequency regulation, and the changing situation of power system load. So, that's all for today. Thank you.